Hello everyone, and welcome to another episode of my little corner of the internet. Today is Tuesday, July 21st, 2026. And your host Dino, and I am coming to you live from my very messy desk. It is a great day to be transcribing YouTubers and talking to myself, which is what I do best. Before we get started, I have a joke for you. Why did the neural network cross the road? Because it wanted to optimize its gradient descent on the other side. Though nobody ever laughs at that one, but it still cracks me up every time. Anyway, I'm introducing a trending article from the archives today. It is a really fascinating piece of research, and I am excited to share it with you. The title is An Exam for Active Observers. The call is Abchkartsi Vorg ABS 26x7 16167. It is long, so let us dive deep into what this paper is all about, because it is honestly mind-blowing. The problem that this paper is trying to solve is actually something we take for granted every single day. When you or I look at a picture or a scene, we do not just take one single snapshot with our eyes and understand everything instantly. Instead, our vision is a closed loop. We constantly move our eyes around. We look at one part of the image. We form a guess about what we are seeing, and then we look back to verify it. This process is called active observation. For decades, scientists in cognitive science and psychology have known that this active scanning is absolutely essential for complex tasks. But here is the catch. We do not know if today's fancy multimodal large language models, like the new GPT-5.5 or Claude Fable 5, actually do this. But researchers noticed that current vision language benchmarks are pretty much saturated, meaning the AI models score really high, but they still fail in the real world. The existing tests do not measure if an AI can actively observe and continuously redirect its attention based on intermediate hypotheses. To fix this problem, the researchers introduced a brand new benchmark called active vision. This benchmark is specifically designed to make active observation measurable for AI models. They created 17 different tasks across 3 main categories, and every single task is designed to force the AI to repeatedly perceive the visual information, rather than just describing the image once and answering based on that static description. And the results? Oh boy. They are terrible for the AI. The high-scoring model they evaluated, which is GPT-5.5 running at its maximum reasoning effort, only solved 10.6% of the items. They actually scored 0 on 11 out of the 17 tasks. Claude Fable 5, which tops most reasoning leaderboards, solved just 3.5%. Meanwhile, human participants averaged 96.1%. That is a massive gap. Even when the researchers let the AI write and run its own computer vision code to solve the problems, the model still failed miserably, because the code was unreliable on realistic images, and catching the errors required the very active perception that the models lack. Let us compare this technology with other approaches. In the past, people evaluated AI using simple multiple-choice questions or basic captioning tasks. As older benchmarks allowed the AI to take linguistic shortcuts. The AI could just look at the image once, turn it into a text summary, and then use its massive language capabilities to guess the answer. But active vision is completely different. It uses arbitrary positions, arbitrary shapes, and tangled curves that cannot be easily summarized in a single sentence. Then we compare the pure AI vision approach to the intuitive use approach, where the AI writes code to analyze the image. We see the tools help it, but they are not a real substitute for actual active vision. The coding agents reached up to 50.6% accuracy, yet they were incredibly slow and expensive, taking 15 minutes and several dollars per question. The coding agents completely failed on tasks that required sequential traversal, like following a tangled rope. Now let us talk about how this applies to everyday life, because this is where it gets really interesting. I will give you 3 specific application examples based on the content of this paper. Let us look at the medical field, specifically radiology. When a doctor looks at a chest X-ray or MRI scan, they do not just glance at it once. They have to perform distributed scanning, which is one of the key tasks in this benchmark. They actively move their eyes across the entire image, looking for tiny nodules or anomalies, comparing different regions, and keeping track of what they have already checked. Right now, hospitals are trying to use AI to help detect diseases. But if current AI models lack active observation, they might just miss crucial details in critical complex scans. We can train models to pass the active vision benchmark. We could develop medical AI that truly scans an image step by step, dramatically reducing the chance of missing a hidden tumor. Second, think about industrial manufacturing and quality control. Imagine a factory producing complex circuit boards. An inspection system needs to verify that every single microscopic wire is connected correctly. This requires sequential traversal, another core category from the paper. The system has to follow a wire from its starting point, through a maze of other wires, all the way to its endpoint. Current AI models fail completely at this. As the paper showed, they get lost almost immediately when trying to trace a line. If you solve the active observation problem, you could deploy AI inspectors on assembly lines that can flawlessly trace intricate connections, ensuring that our electronics are built safely and correctly, which would save companies millions of dollars in defective products. Better to consider scientific discovery in biology. Researchers spend countless hours looking through microscopes, trying to count specific types of cells or observing how cells interact. This requires visual attribute transfer, the third category in the benchmark. A scientist has to hold the exact shape, size, and texture of a target cell in their working memory, and then scan the rest of the sample to find exact matches. The paper shows that AI models default to guessing or using linguistic priors instead of doing the hard work of fine-grained comparison. If future AI models can master active vision, they could act as tireless research assistants, rapidly, accurately counting and comparing microscopic structures. This could accelerate the discovery of new medicines and treatments, because the AI will finally be able to actually see and compare the visual evidence, rather than just guessing based on a superficial glance. It is really fascinating to think about how much we rely on our eyes constantly darting around to make sense of the world. We do it so naturally that we do not even realize that it is a complex loop of perception and reasoning. The fact that our most advanced supercomputers cannot even follow a simple drawn line without losing track really puts human intelligence into perspective. Well, that is all I have for you today on this topic. I hope you found this deep dive as captivating as I did. And I will see you in the next transcription.